most of them related to missile defense target rockets that launch targets out to shoot down the other interceptors. But we have all these rockets under our belt now, and we've got a few strange vehicles too. You're aware of the shuttle, the foam falling incidents on the shuttle. Those were all caught by our cameras up on the external tank. We're up near the nose of the external tank here. And this is the return to flight shuttle launch where they thought they had the foam problem solved, and lo and behold, there was a huge piece of foam that came off. Fortunately, it didn't hit the leading edge like they thought it did on Columbia. But nonetheless, this incident caused the shuttle program to stand down for another whole year until they figured out why they didn't solve the foam problem. And the important thing about this video, besides the fact they just saw, is they got the time that the foam fell off, which was really good to see what was going on. There were something like 100 video cameras on the ground that got the mass into the shuttle. A couple more on airplanes that were chasing along with the shuttle, trying to catch anything that might happen. And none of those cameras saw this fall off, and none of them got the time either, even if they could have seen it. So this clue was very important in figuring out what was causing the foam to fall off in the first place, and eventually they solved the problem by and large. Because one camera on the external tank doesn't get both leading edges of the shuttle, if you look at this other figure, you're really only seeing the starboard wing of the shuttle here. You can't even see the port wing. So after a few launches, NASA decided to put one on each solid rocket booster as well. So we're doing those, or did those until last summer. Getting a really nice view of the leading edges of both wings. So typically on a shuttle launch, we'd have 3 of these going and get really good situational awareness of what's happening. And we all know the shuttle program is done now, but I like to think that the iconic image of some of the shuttle program is this sort of view now. We got some really spectacular stuff, especially at night. This is a night picture. And some of these are very dramatic. This purple sheen on the normally black tiles of the orbiter is caused by the reflection of the blue Earth on the orbiter as it's leaving the external tank. In this view, the part of the Earth is already sunlit, and the ocean's reflecting off that surface. We're also very proud of the fact that we did all the video on Spaceship One with Rocket Cam. These were very simple systems, all recorded except for one channel, which was typically this was typically broadcast live also. These were all recorded on board the recorders. You can see one right here, right behind the pilot, with the flip-up screen to show the pilots when they turn them on just before they taxi, whether the thing was pointing in the right direction. But for Spaceship One, I think these kinds of onboard images are what everybody remembers by. It's not so much the graphic stuff. All of it was really cool. So you remember that, especially this one. It's satisfying to go to the Air and Space Museum and see this thing hanging up there with all the elements coming here. So we're hoping to do something like this with Spaceship Two. A little lesson about branding. Everybody's seen this video from SpaceX Falcon launches, and I've done informal polls at conferences and speeches and stuff, and almost everybody thinks we did this. Turns out this is the only one we don't do, pretty much. And it's a branding lesson. When you get a market penetrated pretty well with your brand, it doesn't really matter if people know for sure whether you did it or not. It's what's important to them. I had people after speeches by Elon come up and congratulate me for the great video, and I said, well, I have to tell them it's not really ours, but thanks anyway. But the guy who did this at SpaceX used to work for us, so it's very similar to our analog video system. It's all good. All this is so we had a limitation with the analog system. We started wanting to get on a spacecraft. It turns out Earth orbiting spacecraft, especially in low Earth orbit, don't get tracked 90 minutes every orbit. It's usually little periods of 4, 6, 8, 10 minutes. And there's important things happening in between, so they all wanted some way to store the video and then downlink it later. And that's not easy if you just turn the video on and do nothing else with it. So we needed to invent some avionics that do that. And we had a need for more sensors besides 2 or 3. We wanted to digitize the video because the analog video is a bandwidth hog. We needed to manage the bandwidth, compress the video as needed. So we had to develop some avionics boxes that would do all that for us. And over the started big and clunky, like this one. We got a little smaller over the years, and then now we're selling one that's relatively small. Size scale. The cameras are the same as what we've used all along. Yeah, and the pen. I'll go into some of these applications just so you get a feeling for it. But what we're mainly doing with this avionics is fundamentally we're managing bandwidth, because bandwidth is a huge problem once you get these sensors moving. There's always bottlenecks somewhere. The second thing we're doing is we're compressing the video sort of willy-nilly as the customer wants it compressed, so we can vary the output depending on what they have available for bandwidth and for other needs like resolution. We also, because we have such a good controller and scheduler in this avionics box, we can do a lot of things like control other subsystem elements. We can control mechanisms. We can control data flow from other sensors that we don't even do, but they want us to control the sensors. So I'll give you some examples of that. First thing I mentioned is compression. Compression is huge for video because you can greatly decrease the total number of bits you're shoving through the pipeline, even though the human eye won't really tell a whole lot of difference. So this gives you a feeling from that same picture. Pretty much uncompressed, you can see a lot of detail there. Even as you go to fairly serious compression, here you're reducing the bit size, total bit amount by 7. You're able to make that out pretty well what it is. After you get really aggressive, it starts fuzzing up on you. But a lot of our customers will gladly accept this if they can just get more data. So we do that. The first example we had of being able to do this on a spacecraft where we had a really severe bandwidth problem was to watch a very extended 4-hour deployment of a very large antenna on a geosynchronous communications satellite. It's commercial for a company called ICO, and the total deployment time was 4 hours. We only had 200 kilobits per second to work with, which is almost no more than a nice frame on your typical small camera that you hold in your pocket. And we had to somehow cover this deployment. It's a dish antenna about as big as this entire lecture area here, 12 meters across. So we put this on a commercial satellite, got a small system that actually had 3 cameras looking at different views of the antenna. And you can see this thing turning out and eventually deploying full width. It worked like a charm. The whole thing was on for 4 days. We're about to do this again on another spacecraft in about 2 months. We did a similar system on a spacecraft called EchoStar 11. It's part of a commercial competitive experiment against DirecTV by Dish Networks. And what they wanted to do was offer a channel that Dish, they knew it wouldn't be offered on Dish. And so what they have, and it's still operating up in the geosynchronous orbit, is this view of the Earth on channel 287 of Dish. And if you haven't seen it, that's because you're not a Dish subscriber. That's the only place you can see it. And the spacecraft is parked over the longitude of Denver at the equator, and it returns this view every day, 24 hours a day, no interruptions, no commercials except for some background music. And you get a little time tag at the bottom that runs along the data, year it is, and what time of day. That's all you see. And the only thing that changes is the weather. The terminator of the Earth goes around and around every 24 hours. And then once in a while you see a total solar eclipse go across the western hemisphere of the Earth. And about every month you see the moon go behind the Earth and walk across the screen and come back again. And it's pretty cool. This is the same view, only synchronized hemisphere, the eastern limb of the Earth. When the sun is directly opposite the spacecraft at basically local midnight, the entire ring of the Earth is glowing like this because there's enough light that comes around and gets refracted. Another fun mission was the LCROSS mission that NASA sent to the moon a couple years ago, 4 years ago now. Needed a controller for all of the sensors they had in mind, and they also wanted a situational awareness video just to see the impact, the approach and impact as they went into the moon. This was directed to the South Pole with the Centaur stage impacting purposely in the depths of a permanently shadowed crater, trying to dig up some dirt into the sunlight. And this vehicle and all the other telescopes that were available monitored the plume as it came up, the dust plume, to see if there was actually water ice in that dirt. And so we did with NASA Ames was they built a payload panel, one of 6 panels on the spacecraft. They have 9 different sensors looking this way and that way from the vehicle. Our avionics box was controlling all of that, and one of those sensors was the video camera right there. Most of the rest of them were infrared of some sort or another. That's a better way to detect us. So in October of 2009, we were approaching the moon, heading for, I think it was somewhere right around here in this crater. I've kind of lost my bearings since then. But that's a snap right off the monitor of the visible video going in. It's really fun to watch as this thing got closer and closer. This is a comparable image as we are even closer of the infrared view. Of course, it's color enhanced, so you can kind of tell what's cold and what's hot. But the cold crater basin is right here, and they were heading basically where this guy's finger's pointing. And it turns out the impact was successful. The dirt plume went up, and all 9 sensors, after they crunched on the data for quite a while, saw the impact and saw the remnants of what was left there. And the end result is, between these observations and orbiting observations from other spacecraft, we now know that on the South Pole and the North Pole of the Moon, there's something like 1 trillion tons of water ice in the buried soils there. And that's a huge impact on future lunar exploration. The most recent mission we're on that's at the moon is the Grail spacecraft. They entered lunar orbit at the end of last year, and the 1st of January. 2 different spacecraft, they're talking to each other with very precise signals. On the spacecraft, there's 4 camera systems, or a 4-camera system on each one that's going to be used for their education and public outreach program. And these are the hardware sets, one on each spacecraft. As the spacecraft go around the moon, they're basically pointing with their face to the moon all the time. And there's 1 camera looking forward about 45 degrees, 1 looking aft, and then 2 looking straight down. And one of the 2 looking straight down is more like a telescope lens. It's more like a very nice SLR kind of lens. And these will start full-blown operations using middle school students as the schedulers for the video and the processors of the video clips, starting this, I think it's next Thursday, March 8th. So shortly after launch, this was a pretty exciting mission for us and for everybody else on the project. So shortly after launch, the systems were turned on to get a sample image from each camera, and we were happy to see the first image come back, which is that, which was looking into nowhere in deep space, and we saw absolutely nothing, which is what we were hoping to see, because the cameras can't detect stars, planets, and the moon, so we knew it was working, so we didn't see anything. Once we got to the moon, they took a few more sample images. This is all from video now. It's not a still image, but it's a video frame from a 30 frame per second video. And you can see at least one of these cameras is working great. So we're looking forward to getting all sorts of interesting video clips eventually on YouTube, I think. That avionics I showed, that's still too big and clunky for a lot of these spacecraft and rockets, and especially smaller spacecraft. So, as I mentioned earlier, we've shrunk this avionics down now so that they're all about this size, and all we do is add more slices if we want more functions. This is sort of the minimum complement of slices. One controls the power coming in from the host platform and distributes all the voltages we need. The other one controls the command and telemetry to the host platform, so we can talk with what we're based on. And then the third slice, this one is controlling 8 cameras in this case. We have another slice that will control 2 high-definition cameras, or 2 high-speed cameras, or a couple of infrared cameras. So you can mix and match these slices and come up with some clever solutions to things. This whole thing, the avionics weighs 700 grams. It's not very heavy, and each camera weighs 200 grams. So coming up this, hopefully in April or so, maybe even later, depending on how the launch pad improvements go, we're on the new Antares rocket for Orbital Sciences. Brand new liquid rocket, first time they've ever done a liquid rocket. And it's going to be launching a cargo vehicle to space station, which will carry not humans, but cargo. And we're on that as well with a video system that will watch the approach as we go to space station. So we're looking forward to that. That's a nice kind of project to be on because we're on both of the vehicles. And helps everything. Here's the complement for the Antares rocket that we'll be using. There's an external pod camera, just like we use on Delta 2 and Delta 4. Got a couple of internal cameras to look inside the payload fairing of the spacecraft as it's going up inside the fairing. Since you can't see anything inside a fairing if it's still on because it's pitch dark, we have lights that will illuminate that whole scene, give you a view of what's up there. And then the basic avionics is the same as what I showed earlier, but we also added a transmitter because they wanted us to take care of transmitting the early data, and we also added our battery packs because they didn't want to supply power. So that's kind of a typical solution. I mentioned Virgin Galactic. We're supporting with a couple of systems right now the flight test program, and that's mostly to support the National Geographic production specials. They have a contract to do 4 specials on this with National Geographic. And we're supporting the producer, providing a couple of high definition and standard video channels. There's, I think, on the total for both vehicles, probably up to like 10 channels of video going all at once. And they come from a mixed bag of sources, but we're getting the job done there. This is, if you haven't seen it, one of the recent flight tests where they feathered the aircraft wings. Those are going well. Can't wait to see the full-blown rocket-powered flights later this year. Other things to look for is the Orion capsule that's being funded by NASA, being built by Lockheed Martin, is supposed to be going through a shakedown flight test on a Delta IV rocket in 2014. Check the whole system in, and we're supposed to be on that launch and supply some situational awareness video of the entire operation. A lot of mechanical things happening, so you can watch that closely. Likewise, for the Boeing CST capsule, it's a commercially developed capsule for commercial crew to NASA to space station. We're expecting to be on the flight test program for that. We're also talking with Sierra Nevada to do some supporting video and data acquisition for their Dream Chaser drop test later this summer. We're going to be dropping it on Virgin Galactic Flight Night 2 and dropping the thing down and landing it on a runway, I think at Edwards, but I'm not sure about that. If none of you are interested in space stuff, we're also on some cool platforms like this car. It's a supersonic car called the North American Eagle. It used to be an F-104 supersonic fighter jet, and now it's a car. And they're hoping to go for a run next summer, summer 2013 at 800 miles an hour or more. The current record is 763. So that's going to be a fun ride if they get there. They're up to, test runs are up to 425 right now. I've been to a couple of those. They're fabulous to watch. A little longer term, it's not clear when Mr. Bigelow is going to get his larger modules up into orbit. There's 2 of them up there now that are subscale models, but we're hoping to outfit some of the larger modules with video. We hear a lot of systems from us, but there's no firm plan to launch these modules yet. Because before he can do that, he needs reliable commercial crew capability, and that's still coming. So these might be 2015 or 16, but not around the corner yet. Other missions we're going to be on, I won't show images of them, but we're on quite a few of the remaining Atlas launches. Some Delta launches are left. We're on several spacecraft, geosynchronous orbit as well as lower orbiting, and quite a few classified spacecraft that we don't even know what they are or where they're going. Classified. That's all. We've got about 6 of those. And we're on quite a few missile defense target vehicles still. There's probably a dozen of those that we're on. And basically launch out of Hawaii, launch a target up to space, and then it's intercepted by some of our missile defense interceptors and shot down. It's all tested. So that's where we are. I'll cut it off there and take questions. Let's go.
Care to comment at all if you can about the regulatory challenges of putting high quality optics in space?
Yeah, it's interesting. When EchoStar approached us about the imaging system to look back at the Earth, much to our surprise, we found out we had to have a remote sensing license to do that. And it's from the Department of Commerce.
Sir.
And, okay. And so to have that system operating, we had to first apply for a license, and once we got the system designed, we had to explain to them what we're going to be looking at and with what sort of optics. We said, these are just little tiny cameras. They don't do any remote sensing per se. And they said, it doesn't matter. You're looking at the Earth. And it turns out even if you're going to land on the moon with a lander, like a Google Lunar X Prize lander and look back and take pictures of the Earth, you still need a remote sensing license. So that's a little weird. Besides that, the only other regulations we have to deal with this are the frequency assignments. And that's pretty important too, because there's a lot of bandwidth coming down. So every single application has a specific frequency band you have to operate in. But other than that, the remote sensing license is all we had. And we had to prove to them once we mounted it to the spacecraft that it was as we designed it and we're looking where we said we were going to look. We believe that's just so they know in case of a national emergency, they know where all the assets are that might be able to give a view of something that they need to look at. So it's interesting. Yeah, slide.
On your digital systems that appear to be integrated pretty tightly with the spacecraft hardware themselves, what kind of data bus protocols do these satellites use? Is it just something standardized?
Yeah, we use standard as much as possible. So we use RS-422, which is a very standard serial data bus. We are starting to work with GIG-E, which is a very common camera bus that goes to our electronics. We have occasionally done other custom protocols when the spacecraft didn't want to change theirs, and we can do that too, but RS-422 is what we prefer. And one thing I should say about these digital systems is what we do is take almost all the complexity of adding video from the on the spacecraft or the rocket. We take the complexity away from the host platform and put it on our side of the interface. So we don't confuse their computer. We just have them turn us on and we do the rest. So it simplifies their lives. One last question.
You said earlier that you digitized the video to save bandwidth.
Yeah.
What kinds of rates did you get before? What kinds of bandwidth did you use?
Oh, there's two ways we can digitize the video, 30 frames a second coming in or whatever. We do that all the time. First way to reduce bandwidth is throw away frames, because that's too much video sometimes. So on this Earth viewing image, for example, we only had 200 kilobits per second to work with, so we only kept one frame every 15 seconds of video, because nothing's moving down there very fast. So that's the first way. The second way is just compress the actual frame and crunch it down. We can reduce the bits by a factor of 10 easily. So whereas our box could easily put out 100 megabits per second, we're typically throttled back to like 1 or 2 megabits per second, or less. Well, it's typically 1 or 2 cameras flowing video at once, and we switch between them. The most we can do at once is 4 right now, but we're still having to live within about a few megabits per second.
Okay. Well, a round of applause for that.